Hi, welcome back to my channel. This is the next in my series of videos on the Racket programming language. And today we're going to talk a little bit about vectors and how we could use them to make a deque structure. So basically a vector is something that can be accessed by index in basically a constant time. So unlike a list where I'd have to walk through the values of the list the further I get into it, a vector is a contiguous space of memory. And so accessing the third value in a vector is no more different than accessing the fourth or first or whatever in terms of efficiency. The other interesting thing about vectors is that unlike lists, vectors by default, each individual value inside a vector is mutable. And so I'm going to show this here. So one of the things I do in this simple program is I've defined test vector to be a vector of 1, 2, the string foo, and 4. Now, note vectors in Scheme, unlike, let's say, arrays in other languages, can be an array of anything. It's not just an array of integers, an array of strings. And that has advantages and disadvantages, obviously. You could be more efficient if you knew that a vector was an array of all the integers. You would pack them in more tightly, and you would have less, basically, pointer dereferences. For those that know about this, how you would do it underneath is you wouldn't have to dereference a pointer for every entry inside the vector. So let's run this. And again, we do vector ref, so we get the second item out of it from test vector. Gives us back foo over here. Let me just make this a little bit bigger. Yep. And now we set the second value. Well, in this case, the third value. Vectors is 0 indexed. So the third value in the vector to be 3, and then we get it again, vector ref text vector 2, and now it's 3. So the insides of vectors are mutable. So that's interesting. So what I'm going to do here is I'm just going to give a simple example of how we could do a well-known data structure using this fact to kind of create the building blocks of a deque. And what a deque is it basically is a data structure in which, like a stack, you can push and pop off of it. And like a queue, you can enqueue and dequeue things from it. But both of those operations should be fairly efficient. And what I mean by that is that it should not take longer to enqueue something based on the length of that queue. It should be a constant time. And so, unlike a linked list, for those of you who are more familiar with algorithm and data structures, where a linked list, if you wanted to do linked list for a queue, you have to go all the way to the end. We're going to do something slightly different. And what we're going to do is that we are going to fundamentally use the linked list concept for this, but we're going to basically use track basically where the first item and the last item is in that list to make those operations more efficient. Now, to emulate this linked list node, I've defined this deque node as the following. I'm making it a vector where the first value is going to be an arbitrary value, and then by default, it's an empty list. This is going to be where this next node is going to be. So referring to the next node is going to be right here. So now, I've now just created some basic helper values to get the value out of a deque node and get the next node from a deque node. And now I've defined it as the following. I'll go ahead and said I'm going to do set the deque node next. So I can change now the next by using this vector set for that to be 1. And now I'm going to now I have the node. Now what I'm going to do is I'm going to define this deque as the following. It's going to be a vector of 3 things. It's going to be a vector of the length, and it's going to have these 2 empty things. This is going to be where the first node lives, and this is where going to be the second node lives. And then again, I have some other helper functions for getting the length, incrementing and decrementing the length of the queue, and basically setting the first element of the queue and setting the last element of the queue. And Basically, what I'm going to do is the following. The deck, to push things onto the deck, if it's 0, this is fairly simple. I make a new node, and I set the first and last part of the deck to both refer to that new node value, right? And then I'm going to increment the length of it to be 1. Otherwise, if I'm pushing, all I need to do is the following. I need to get the first node, so what was the first beforehand, and what I need to get the new node. And create a new node. And then what I need to do is I need to set the next part of that first node, the next part of the new node to point to the first node. So what I'm doing is I'm saying, okay, this new node points to what was the previous first value, and then I set the first value of this deck to be obviously that new node. I'm pushing it into the front, and I increment the length again to keep track of things. So to pop, it's fairly simple. It's fairly straightforward. If the deck length is 0, I throw an error. You can't pop from an empty deck. Otherwise, if the deck length is 1, then I just simply do the following. Grab the value from the first node, deck first here, deque, and then set both the first and last to be empty, decrement the value of the length in the deck, and then just return that value. Otherwise, here's what I need to do. I need to first grab the first node here, right? The value of this first node. Then I set the first value of the deck to be the next, what the first node pointed to next. So the next in this list, right? Then I can decrement the length, and then I can return the value of that first node that I first set here. So what I'm doing is I'm grabbing what's at first so I can get the value of that out later, but then I'm modifying the deck so that the first part of the deck points to what the first node's next node was going to be. So I'm basically moving one down the list. Now to enqueue, I do something slightly different. Again, if it's empty, what I do the following is if it's empty, I go ahead, set the new node, create a new node value, go ahead and set the first and the last to the new node, and then I'm going to increment the length of the deck. Otherwise, I'm going to get the value of the last node, and I'm going to create a new node with that value, and I'm going to set the next of the last node to point to the new node. I'm adding now to the back. And now I go ahead and say, okay, set deck last to be the new node. The last part of it is now this new node, and I now increment this length. One of the reasons I keep tracking of the length is it does help with the logic a little bit, so they don't have to check for certain types of things. But also, in this case, I want to be able to ask what the length of a deck is and not have to go through and figure out, transverse every single type of where things are in the list. That would be very expensive. So I just want to be able to have a little field here and says, oh, well, this list has this length here. Okay. Now, the interesting thing about this is that dequeuing, or removing something from the queue, is the exact same as popping it. It's just removing the first item. But I also can do two things now, is I can also allow people to peek at the front and then peek at the back. And basically, all this does is it checks to see if the deck has a length 0 that says it's an error. You can't peek at a deck that's empty. Otherwise, just give me the value of the first part in the deck, the first node in the deck. For back, it's just the same thing, except I just give me the last value. And what I've done here is I've created a bunch of things where ultimately it's just a series of values that I'm running. And if I run it here, I put in Q2, I've pushed 1 and 0 on there, and now I've popped off, and I've gotten to 0, which is what I expect. Right? Now I've enqueued 3, 4, and 5, but I've pushed 0, and now I've done a bunch of pops, and of course it's now 0, 1, 2, 3, 4, 5, and at the very end the length is 0. So this all seems to be working very well and very efficiently. So now this is maybe not the best way to do this. Racket also has a notion of structs that we'll get into later, so that we can actually assign like fields, and it creates a lot of these accessors and getters and setters for us. But it's good to kind of look underneath and see how this vector concept allows us to implement something that looks a little bit more like a struct in C, or even if you think about it, like a struct in C or a struct in C++, or even what we would start to be as a class. And by using the vector to say, okay, we have basically a contiguous area of values, each of them pointing to a specific value here. And so that's what we've used here so far. Again, we're using some basics around basically, we are having to use mutability, or taking advantage of the fact that vectors are mutable. And that makes that operation very efficient. Now, one of the things that's interesting is that some people might argue that this is not quite correct, that when you think about it, all of these push, pops, NQs, and DQs should have exclamation points after them. And there's certainly a good argument for that. And it's one of those things where, unfortunately, Racket kind of seems to go hand in hand. Kind of seems to go on not strictly enforcing this for some things and using it for others. It's an interesting convention. You just kind of have to use what's best for you. You can make arguments for both. A lot of people only use this to really catch that there's doing things like if there's a set or a setter, then you put the bang exclamation out. Otherwise, if it's a more complex operation, you actually don't want to use it. There's arguments for all that and stuff like that. So that's a matter of style. So now that we've looked at this and we've looked and see how we can do these kind of efficient types of things, one of the things I'm going to now go back to is that in the next in the next video in this series, I'm going to discuss the notion of purely functional data structures and what would happen if we needed to do something like a deque or a queue, and we didn't have this kind of mutability, and all we had was kind of a list. How could we make that efficient compared to have as efficient or somewhat efficient compared to having a mutable type of data structure? So we'll discuss that in the next series, and look forward to seeing you in that video.